All right, so what I would have done, I probably wouldn't have used elimination because it's already set up as substitution, so I would have just taken this 2x plus 3 and plugged it straight in for that y. Which would give me negative 4x plus 2 times 2x plus 3 equals a negative 6. That will give me negative 4x plus 4x plus 6 equals negative 6. These will cancel out. I'm left with 6 equals negative 6. So the first thing I'm looking at is the fact that my variables dropped out. As soon as my variables drop out, it's either all solutions or no solutions. So either it's dependent or inconsistent. Since this is a false statement, this is false, it means that it must be inconsistent. C, inconsistent is your answer. Any questions on that? Make sure you know how to do those. Don't lose simple points. So we need to know how to do substitution, elimination, and we need to know how to read graphs. I'm going to say that right now because we're probably not going to spend a whole bunch of time going over this again. Because we're going to focus mainly on matrices. And Charlie's excited about it for some reason. I love matrices. I love matrices. They're very mathematical. All right, so first of all, a matrix is just a rectangular array of real numbers. And array just is a fancy word for arrangement. Ooh, we're not writing today, are we?
Well, at least the words.
Right? That was a whole thing yesterday. I had to figure out what port it uses. I don't know what port it uses. Okay, so it's a rectangular arrangement of numbers. And we have two sets. We have rows and we have columns. And a lot of times people struggle with which is my row and which is my column. So I always find my columns first. And the way I get columns is I think of like a coliseum or columns of a building. A column goes up and down. It supports a roof. So that means our column must be these. So I always find our column first. It's the ones that go up. And that means we have 1, 2, 3, 4, 5 of these guys. Which means the other ones are rows. And we have 3 of those. And now we come up with the size. And the size is always which one goes first and how do we do it. So we always go rows before columns. We do rows before columns. So this is going to be a 3 by 5 with rows first and columns second. So I was rows before columns. And so that's a 3 by 5. I think that's the easiest things get mixed up with matrices. It's the easiest points to miss on a test. Because there will be questions that just say, how many rows, how many columns, give me the size. It's just keeping everything straight. Columns go up and down, just like column of a building. So that must mean rows must be the ones that go this way. And then we also have rows before columns. All right, we're supposed to determine the size of each of these matrices. So the first one, it has 1 row and 3 columns. Remember, columns are up and down, so this makes this a 1 by 3. Our next one has 3 rows and 1 column. So it has 1 going up and 3 going horizontal. So this is going to be a 3 by 1. This one's always a nice one to see because even if you mix it up, it's still a 2 by 2. There's 2 rows, 2 columns, so it's a 2 by 2. And our final one is going to be, I forgot how to do this. Can someone tell me how to do that? What's the last one? Yeah, Teresa. What? 3 by 2. Yeah, perfect. I thought you said 2 by 2. I'm like, ooh. It's a 3 by 2. And that's how we list them. These can easily be on the test. What is the size of it? Easy points to miss if you just don't take your time. Practice, study these. Make sure on the test you just at least for a little bit, go over this again on how to do it. It should be easy points on the test. All right. More importantly, because we've seen matrices before in Algebra 2, so we're not going to go over the whole basics of it. We're going to go right into the augmented matrix. And the augmented matrix is what we're going to actually use to solve systems of linear equations, because an augmented matrix is a system of linear equations. It says all the same material in the exact same order. It's just nice to work with, and it's easy to plug into our calculator, and that's what we're building to next Tuesday. Bring your calculators, because we will be using our calculators to solve these, and your life will be a lot easier. So the first thing is, we're going to represent any system of linear equations as an augmented matrix. And with this augmented matrix, we are going to have coefficients, and we are going to have constants. Our coefficients are always going to be on this side. Remember, a coefficient is just a number in front of a variable. So these are all our coefficients. So A, B, C, D, we'll always have coefficients on this side of that bar. So these are our coefficients. And the other side of the bar this will actually be our equal sign, and we'll always put our constants. So we'll not have any more variables over here. So we're going to put all of our constants over here. So that means before I do anything else, if I'm dealing with systems of linear equations and matrices, I'm going to make sure all my variables are on one side and all my constants are on the other side. That's going to be the first thing you need to do if you're going to put something into a matrix. So for example, you got to have your E and F and all your X's and Y's on the other side. In fact, I think that's the first thing we're going to do in this problem here, because it says write each of these as an augmented matrix. It says x equals y plus 3 and y equals 4 minus x. The little note down there says you have to have all your variables on one side and all of your constants on the other side. Currently, we have variables on both sides. So not only are we going to move all the variables to one side, we're going to put them in the exact same order. So we're going to put all of our x's first, all of our y's second. If we had z's, we'll go z's. If we had smiley faces, all the smiley faces. You just keep everything in a straight order. So for example, we're going to move the y to the other side. So we're going to go y, or x minus y, equals 3. I just subtracted y from both sides. On the next one, we're going to have it as x, so I'll add x to both sides, plus y equals 4. Note all of my x's line up, all my y's line up, and all my constants line up. Having it written like this is going to make writing the matrix a lot easier, because we can kind of picture this as just being 1 in front of the x, a -1, a 3. A 1 in front of the x, a 1 in front of the y, a 4, and that's exactly what our matrix is going to look like.
You just want to separate the variables from the
Not the coefficients. Yeah, I'm actually pulling out the coefficients, because we aren't going to put x in these columns. What we're going to write here is we're going to write, well, I have 1x. This spot right here tells me I have 1x. And then we go over and say how many y's I have. So I have -1 y's. And this bar is just like my equal sign. So this, honestly, reads the exact same thing as your system. This reads right now 1x plus -1y, or minus y, equals, and it's going to equal 3. Then the bottom one is 1x plus 1y, so it's a +1, equals 4. So what can help people with augmented matrices, if you can't quite read what's happening, is you can put an x and a y up on top. You're not required to. It just can sometimes help you read it, that this is saying 1x minus 1y equals 3. The bottom row says 1x plus 1y equals 4. So they're just saying how many x's and y's we have and what they equal. That's all that's happening here. Make sure you account for all your variables when writing an augmented matrix. If you look at the top row, I have x's, y's, and I have z's. The middle row says 2x plus 3z equals 5. It didn't talk about y's. So how many y's do I actually have? Yeah.
0.
I have 0 y's. You have to make sure you account for those 0 y's. There's two ways to do it. Either do what Mike just did and just said, hey, I got 0 of them, make sure in the matrix I put 0 of them. Or you can rewrite it. You can rewrite it in order to have it basically go x plus 2y minus z equals 1, so I don't have to change anything there. Here I line up my x's, and I have a blank here. I have a blank here. So I just fill in that blank with 0 y's. And line up my x's and y's down here, minus 2y plus z equals 0. Now I have all of my variables lined up. I got all my x's, I got my y's, I got my z's, and I got what they equal. And you can picture your matrix right now. That it'd be 1, 2, 3, 2, 0, negative 2, negative 1, 3, 1, 1, 5, 0. Now it's just writing it as a matrix. So we'll go below and write that matrix. In that first system, I have 1x, so I'll put a 1. I have 2 y's, so we'll put a 2. I have negative 1 z's, and that's going to equal 1. My second row is going to be I have 2 x's. I have 0 y's. I have 3 z's, and that's going to equal 5. And finally on the bottom I have 3 x's, negative 2, 1 z, and 0. So you can either rewrite everything so you line it up, or once again you can just ask yourself, or you can call this my x column, my y column, my z column. Look at the original one and see how many you have of them. I have 1x, so in the column I should have 1 x's. In the second one I have 2 x's, I have 2 of them there. In the third one I have 3 x's, I have a 3 there. Everything matches up. So once again, an augmented matrix is the exact same thing as a system of linear equations. You can read this the exact same way. You can say, well, this is x plus 2y minus z equals 1. It's just an easy way to write it without all the variables. It allows us to solve it in completely different methods, and it allows us to plug it in our calculator. All right, let's move down. The next one says write the system for each augmented matrix. So this time we're starting with an augmented matrix, and we'll write it as a system of linear equations. So just remember that we have an x column and a y column. So that top one is really saying, well, 1x plus 0 y's equals 5. And that bottom one is saying 0 x's plus 1y equals 1. In other words, x equals 5 and y equals 1. Looks pretty basic, but that is the key behind solving systems of linear equations using matrices. It is this fact. This, and we'll have it written on the other side, is called the identity matrix. It is a matrix that has 1's diagonally and 0's everywhere else. Just like this. As soon as you have an identity matrix on your left-hand side of your augmented matrix, you have your answer. You know what your x is, you know what your y is, you know what your z would be. Because if I had a third column, I'd have another 1 and some more zeros. And that will be the backbone of what we talk about in our next section. We'll put a pause on that for just a second. All right, our next one, write the augmented matrix as a system of linear equations. So once again, we just say, well, if I picture this as being my x column, my y column, my z column, my first one's going to be 2x plus I have a positive 3y plus 4z. That's going to equal 6. Our next row is going to be negative 1x or negative x plus 0y. If you don't want to write the 0y, you do not have to. Plus 5z equals negative 2. And our final column would be a positive 1x, or just x, minus 2y, plus 3z equals 1. Like I said, you could just skip that 0y too. You could, if you wanted to, just left that blank, and you could have shifted everything over, or you can leave it in there. Not a problem. Questions on writing either direction? All right. When we're solving systems using matrices, we have to, just like when we use substitution, elimination, or any other method, we kind of mess with the numbers a little bit. We make sure everything stays balanced, but we have to change the way it looks. There are certain row operations we're allowed to do that keeps everything balanced. Just like with any kind of system equation, you could add 2 to both sides, it stays balanced. You can multiply by 2, it stays balanced. In elimination, you can add the two things together, everything stays balanced. These are the 3 things you are allowed to do to any matrix, and it remains balanced on both sides. So the first thing we're allowed to do is we're allowed to flip rows. We're allowed to flip rows, and why we're allowed to do that is because if I have 2 systems, so picture that x plus y, or x equals y plus 3 and y equals 4 minus x. If I read that to you in a different direction, does that change any of the values? If I'd put this y equals on top, it wouldn't change any values. That's all we're doing. We're just switching the order that they're done in. So our very first thing we're allowed to do is interchange 2 rows. The big part about this is how to note you did this. In order to do a row operation, because we're going to be doing a whole bunch of them and I need to know what you did and you need to know what you did along the way too, you are going to list to yourself and the reader what you're going to do, and then you do it. So we're kind of writing a little sentence to ourselves. So I'm going to flip those 2 rows. And how I'm going to note that is I'm going to say, well, I'm going to take row 1. So right below it, I'm going to say, I'm going to take row 1. And I'm going to flip that or interchange that with row 2. So this little double angle is basically saying, I'm going to replace row 1 with row 2, and I'm going to take row 2 and replace it with row 1. That arrow goes both directions. So you have to write that, saying that you interchanging those 2 rows. Then we can actually do the work. So interchanging those 2 rows, our row 1 becomes our row 2, and our row 2 becomes our row 1. So on the top, we're going to have negative 1, 3, and 2. And on the bottom, we're going to have 2, 4, and 8. Although not the most used of these row operations, it can be very helpful when you want to put a specific number in a specific place, which we'll see on the next page. So that is interchanging 2 rows, 100%. I'm okay with that. Next thing is you can multiply every row or every element in a row by a non-zero real number. All this is saying is you can multiply both sides of an equation by 2 or 3 or 4. The only thing you can't do is multiply by 0, because then you have 0 equals 0 and you just ruin the whole thing. So we can multiply, let's just say, I'm going to multiply that first row by 2. I'm going to multiply that first row by 2. Once again, we have to say what we're going to do, and then we're going to do it. So the first part of this is pretty easy. It's just say, hey, do 2 times row 1. But now we have to say where we're going to put that. Where we're going to put that. And what I mean by that is we're going to go 2 times row 1, replace row 1 with those values. All right, this is just saying I'm going to do something. This is saying where I'm going to write it. So I'm going to do 2 times row 1. I'm going to write it in place of row 1. So this is just something happening. This is where I write it. So 2 times row 1, well, 2 times 2 is going to be 4, so we're going to replace row 1 with 4. Then we'll do the next element, which is a 4. We'll do 2 times 4, which is 8. And finally, we'll have 8 times 2, which is 16. I replaced row 1 with that. I didn't even talk about row 2, so row 2 is going to stay the exact same. Since I can multiply, I can also do division, but most of the time when we talk about division, I would just say multiply row 1 by 1/2 and replace row 1 with it if I wanted to do division. And we'll do that in the next problem. Or not the next problem, but on the back side. All right, the last thing I'm allowed to do is, remember with elimination where we stack them together and then we add them together, eliminating like a variable? So that means we can add two systems to each other because they're balanced and everything remains balanced. So I could do row 1 plus row 2 and replace row 2 with that fact. In addition to that, I'm allowed to add a multiple of a row to another row. And how that might look is, let me just set up the premise. I'm going to take row 1. I'm going to multiply it by 2. I'm going to take row 1, multiply it by 2, and I'm going to actually add it to row 2. So I'm multiplying this by 2, adding it to row 2, and I'm going to replace row 2 with whatever I get. A good thing to keep track of here is whatever I'm adding to is generally the row you're going to replace with. So if I'm multiplying a row by some number and adding it to another row, we're going to replace that row I'm adding it to. That's the one that's going to be replaced. So now we have to do a little math in our head, or you could do a little scratch work, because we're actually going to take each element. So I'm just looking at, let's just focus on this 2 and that -1. We're going to do 2 times row 1, so that's going to be 2 times 2 is going to give me 4, and then we're going to add it to -1. So we're going to do 4 plus a -1, which is going to be 3. And I said I'm replacing row 2 with that. So in fact, since I'm replacing row 2 and I'm not doing anything to row 1, I'll probably write row 1 because I'm leaving it alone. I'm not replacing it, I'm replacing row 2. All right, let's go ahead and look at that 4 and that 3. 4 is in row 1, so I'm going to do 2 times 4, which gives me 8, plus that 3. 8 plus 3 is going to give me 11. And finally, let's look at that 8 and that 2. What other color do I have? I got purple. We're going to look at that 8 and that 2. Once again, we're multiplying row 1 by 2, so it's 2 times 8 gives me 16, plus that row 2 number, which is 2, so it's going to be 18. When these get really complex, it's always a good idea to write little notes to yourself. Right? If I'm doing like by weird fractions, like 2/3 times something, you may want to do all of row 1 and go, well, 2 times 2 is 4, and write 4 above it. 8, 16. I just didn't want to do it here because it looks a little messy, especially, but I might do something like this, 4, 8, 16, and then I'll add it to the row 2. Just write little notes to yourself because it's very easy to make little mistakes in these because we'll have lots of numbers floating around. Any questions of any of that? Are we good? Are we okay? Let's move on. Gauss-Jordan elimination method, you need to know the term Gauss-Jordan. You don't have to memorize it, but you have to know when seeing Gauss-Jordan, you're going to use this method because we're going to learn another method as well. So if I say Gauss-Jordan, you have to use this method. And this method is based upon the fact of the identity matrix. So we're going to solve a system using increasingly simpler equivalent augmented matrices. And then we're going to use row operations to obtain an identity matrix. So the big two words in this one are Gauss-Jordan elimination method and identity matrix. An identity matrix, once again, is just a matrix with ones in a diagonal and zeros everywhere else, where the top left is always your first one, and we go down just like this. So that's an identity matrix because of the ones in a diagonal, and everything else is 0. And with an identity matrix, we actually have an answer. because this is 1x equals whatever a is, and we have 1y, whatever b is. If we had a z value, we'd have one more 1 down here, bunch more zeros, and we'd have what z equals. So the whole backbone of Gauss-Jordan elimination is the identity matrix. That's why you got to know those two terms. They're synonymous with each other, Gauss-Jordan and identity matrix. The other method is going to be inverses, doesn't use identity matrices. So we need to know Gauss-Jordan, identity. All right. So let's put this in practice. So we're going to solve 2x minus 4y equals 16 over 3x plus y equals 3 using matrices. And we're going to use the Gauss-Jordan method. Gauss-Jordan means I need an identity matrix. So we need something that looks like this. An identity matrix is going to have 1, 0, 1, and an a value and a b value. So I need to turn this into something that looks like this. Right now we do not have this. I'm going to write what we have right here. I'm going to write that as an augmented matrix. Our augmented matrix is going to be, I have 2 x's, negative 4 y's, and that equaled 16. And then we'll have 3 x's, 1 y, and 3 is there. That is my augmented matrix. I want it to look like the identity matrix. I just want 1's slanted, and I want 0's on everything else. So we're going to use these steps to actually use this Gauss-Jordan to turn it into identity. The first step is work left to right. Until our very left column is done, which means this needs to be a 1, this needs to be 0. Until it's done, I will not look at anything else. We're just going to focus on this. All right, so we're working left to right. Next thing says locate which value needs to be 1 and use multiplications to make it a 1. That's kind of a misnomer. We want to make this 2, 1. Trying to think. I think tomorrow we're going to see an example, or not, on Monday we'll see an example of this. If this happened to be 1, we can always flip the 2 rows and we have a 1 there. But for right now, we are going to use multiplication to turn this 2 into a 1. And to turn a 2 into 1 using multiplication is just multiply 2 by 1/2. We're going to multiply 2 by 1/2, but I'm not allowed to multiply just 2 by 1/2. I have to multiply the entire row. So we're doing the entire row multiplied by 1/2. And we are going to replace row 1 with whatever we get. Remember, for all these, you will always have an arrow and tell me which row you're replacing. So we're doing 1/2 times row 1, and we're replacing it with row 1. So that's going to look like this. Well, 1/2 of 2 is 1. 1/2 of negative 4 is negative 2. And then 1/2 of 16 is 8. And our bottom row I didn't do anything with, so let's remain 3, 1, 3. So realistically, I just multiplied the top equation by 1/2. That's all I did. All right, I got my 1 taken care of. Now we go into the next step. The next step says use rows operations to make all other values in that column 0. Well, we only have one other number in this column that isn't a 0. So we're going to focus on that 3. And we're going to make that a 0. In order to do that, we're going to use the fact that I can multiply row 1 and add it to row 2. So what we're going to do is we're going to say 1 times what would be an opposite pair to 3. And that's going to be a negative 3. I'm going to multiply row 1 by negative 3 because that's going to give me a negative 3 here. And then I'm going to add it to row 2. Because it'll be negative 3 plus a positive 3 will give me 0. So we're going to add it to row 2. And generally if I'm adding it to a row, I'm going to replace that row with my results. All right, so let's do the multiplication. We'll do it column by column. So negative 3 times 1 is negative 3. In fact, let's just skip one step because I'm not replacing row 1, so I'm going to write row 1 again because I'm not replacing it. I'm just doing something in row 2. And then I'm saying negative 3 times 1. So let me highlight that real quick. I'm just focusing on that at first. So negative 3 times 1 gives me negative 3 plus 3 is going to give me 0. Move to the next one. That is that 2 and that, or negative 2 and 1. We're going to do negative 3 times negative 2, which is a positive 6, plus 1 gives me 7. And finally, we have negative 3 times 8. Let me highlight that again. Let's use blue. Negative 3 times 8 is negative 24, plus 3 is a negative 21. Did I lose anyone yet? Because it gets a little confusing because we're doing a lot of stuff in our head. All right, we are done with column 1. So repeat with next column. Now we go to the next column, the negative 2 and the 7, and we go back. So we locate which value needs to be 1. The 7 needs to be 1. Nope, you'll see. That's why we specifically do it column by column, because I can't mess anything up here. And you'll see why. If you would do it out of order, it would. If you do stuff out of order, like if I would try to make the 0 first, you'll start adding stuff, and all of a sudden you'll mess up these first 2 columns. If you do everything right, this first column will stay 1, 0. So the first thing I'm going to do is I'm going to make that 7 into 1. In order to do that, I'm just going to do 1/7, or 1 over 7, times row 2 will become row 2. Getting your 1 is generally pretty easy. It's just multiplying by whatever fraction makes it into 1. I'm going to come down here and I'll complete it down here. So we aren't doing anything to row 1. So row 1 will stay exactly as it was. So it'll be 1, negative 2, 8. But I'm doing 1/7 of the bottom row. Well, 1/7 of 0 is still 0, so I didn't affect that. 1/7 of 7 is going to be 1. And negative 21 divided by 7 is going to be a negative 3. All right, the very last thing I need to do is create everything else in that column and turn it into a 0. Ooh, I didn't give myself too much room. I'm going to boost that up just a little bit. All right, in order to turn that to a 0, we're going to multiply the other row, so row 2, by some number that creates a 0 pair. So we'll do 2 times row 2. I'm going to add that to row 1. Because now I'm going to have 2 times 1 gives me 2. Add to row 1, that will give me a 0. Whatever I add it to, I'm going to replace that row with. So we'll have replace row 1 with whatever I get. And this should be our last step. So 2 times 0 equals 0 plus 1. It remains a 1. Right, Charlie? So do you see how it didn't affect anything? Because I have 2 times 0. Everything should stay the same. 2 times 1 is 2, plus a negative 2. That gives me my 0. And 2 times negative 3 is negative 6, plus 8 is going to give me 2. The bottom row did not change, so 0, 1, negative 3. This means that x equals 2 and y equals negative 3, and that comes from that. That comes from that, because that's my x column, that's my y column. I am done. Any questions on any of those steps? I reiterate the fact that Charlie brought up a great point. If you do this incorrectly, you're going to start messing with numbers you found. So if you found your 1 and 0 and you start doing weird stuff over here, that 1 and 0 are going to change numbers and you have to go back and fix it. So you have to follow these steps. Otherwise it becomes a really hard jigsaw puzzle that everything's changing as you're doing it and you can't quite figure it out. You don't have to do any of this in your homework. The homework's pretty basic. This just sets us up for Monday, so Monday's lesson go a little quicker because we're going to use a bigger matrix. So you kind of know what the setup's going to be and what we're doing. So you just have a start for that. Any questions for me? This really is right here the backbone of everything we're doing for the next couple days. All right, let's get our homework done, check our answers